I think we should just get started. Hopefully everybody can see my screen. Hello, my name is Haley Capone. I am the Wheaton Women in Ocean Science Scholar, residing or currently coordinating with CCMI, for the past two-ish years I've been on the project. Yeah, I'm really excited to be here, speaking about blue carbon pathways in the Cayman Islands. Previously I was working at the National Oceanic and Atmospheric Administration within their Office of Habitat Conservation, specifically as a marine habitat resource specialist focusing on restoration programs in the Gulf of Mexico. And so yeah, currently, I'm just really excited to be continuing some earlier project work that I had started during my master's on thermal tolerance in seagrass communities on Little Cayman. So really excited to be back, and thank you so much again for your support. So I kind of wanted to start off by describing what blue carbon is. Essentially, you've heard terrestrial ecosystems store carbon, they take it from the atmosphere, and in return, they produce oxygen. So they really provide this valuable ecosystem service that we all, naturally take for granted, as oxygen breathers. But actually, surprisingly, the ocean is this quiet, source of carbon sequestration as well, specifically within coastal ecosystems, where you have a lot of sunlight, a lot of productivity happening, within those communities. And so, a couple examples are seagrass meadows. So, majority of what we'll be talking about today, mangrove forests. So the Caymans also have, mangrove forests as well, equatorial forests, and salt marshes. And so even though these ecosystems cover less than 1% of the ocean floor, and actually seagrass meadows themselves cover about a tenth of a percent of the ocean floor. Almost nearly a fifth of that oceanic carbon is buried by these seagrass communities. So that just speaks to their overwhelming importance in the carbon cycle, in kind of becoming a resource, for, carbon capture. And this just becomes pretty relevant in the context of climate change. Obviously, we all know that's intensifying. CO2 is up in the atmosphere, creating some sort of, as a greenhouse gas, it's making the planet warm. And specifically, small island nations are unfortunately the most vulnerable, to, consequences of climate change, like sea level rise, pollution and flooding events, and also just extreme heat since they are right on the equator. But perhaps notably, these are also some of the most productive carbon-rich systems because of their equatorial, relevancy. So I think they provide this sort of natural-based solution or nature-based solution, that can be harnessed because they can really effectively capture carbon from the atmosphere and lock it away, beneath their roots. And so I think the first step in kind of identifying how we can go about offsetting our carbon is determining how much there is, how much potential there is in the system itself. And so if we can actually measure how much carbon or seagrass meadows store, we can, work to protect them with evidence. So this not only protects that pathway, but also the biodiversity of the system. These systems are a lot more than just the carbon output or the carbon offset that they can provide. They also provide habitat for a lot of nursery species, also help generate carbon credits that can help fund these conservation activities, restoration of seagrass meadows in areas that may be degraded. And then lastly, work to create a financial model where companies are able to help offset their carbon and incentivized to do so through contributing to this blue economy and providing funding that can keep these restoration projects going and ultimately make a healthier, happier environment for both people and the ecological communities to exist. And so the Cayman Islands are in a very particular situation to kind of lead the way on this model. And specifically, um, through the creation of this Blue Carbon and Biodiversity Program, through support by Butterfield, essentially back in 2023 is when this kind of got a hold and started up. And essentially, the two main outcomes or aims of this project going forward have been one, to overwhelmingly quantify how much carbon is being stored in these seagrass meadows, and two, not only that, but whether or not coral reefs restoration can actually enhance this carbon trapping or the sediment trapping around these seagrass meadows to enhance carbon sequestration. And so we're investigating this in a couple different ways. Firstly, just how much carbon is being stored in seagrass meadows, looking at different factors that might influence the uptake of carbon, dissolved inorganic carbon from the environment, such as climatic stress. So, does temperature influence this rate of uptake? Also, again, whether coral restoration nearby meadows can help with this sediment trapping. And lastly, if there's any sort of pathways between ecological communities. So, whether carbon moves from mangrove systems to seagrass systems and how, these systems can work together to support biodiversity, and how improving these processes or learning more about them can actually enhance our understanding of, biological connections in the system. And so I'm going to actually walk through a couple of our major findings that have happened since 2023. And so you might have already heard a couple of these from previous updates, but hopefully we can give you a little more information today on kind of this foundation and where we're looking towards over the next couple years of the project. But finding one pretty early on showed that seagrass meadows in Little Cayman actually store more carbon than we had expected. And so this research came from a study with Florida International University through specifically the CARICAS network or the Caribbean Carbon Accounting in Seagrass network. And it's a regional network consisting of 76 different sites along the Caribbean. I think 21 different institutions participated in this. And essentially, the results were pretty striking. So, researchers came and took sediment cores from the first 30 centimeters of sediment in these seagrass meadows and found, on average, that sites at Little Cayman, specifically Point of Sand, Kingston, and right outside CCMI, stored on average about 40 megagrams of hectare, and that was scaled, per hectare. And that's about 74% higher than the global storage of seagrass meadows. So this is including temperate regions, but also, for Caribbean regions where the storage was around 37.1 megagrams. And so this is important because essentially Little Cayman is at a pretty good place in terms of its ability to store and capture carbon from the environment. And so when you kind of add all of these hectares up with the prevalence of seagrass that exists, that's a lot of carbon that it's, actively sequestering and holding beneath the sediment. So this was a very promising finding, especially in the context of making this carbon offset model. And so I actually got my start at this point with finding two on a study, Davis et al., that we recently published, but essentially found that Caymanian seagrasses are generally pretty thermally hardy. And so, one of the questions that comes about with doing these sorts of carbon studies is whether uptake rates change with warming temperatures, how temperature influences the rate of uptake from dissolved inorganic carbon in the environment towards tissue growth. So turning that carbon into organic carbon as canopy height increases, and how much of that carbon is actually being sequestered at what rate. And so we did this experiment in 2023 on the three dominant seagrass species, so Thalassia, Haliduli, and Syringodium. And so, turtle grass, shoal grass, and manatee grass are the common names, but we did them inside these chambers, as you'll see on the right, closed systems measuring oxygen change and temperature. So we ran them from about uh, 15 degrees Celsius, 16 Celsius to 35. And, at 15, 20-minute intervals per temperature. And essentially, we found that peak photosynthesis for all three species was around 30 degrees Celsius, as you can see by the blue shaded line in these graphics with respiration shown in the tan. And so we're interested in this case in photosynthesis because that's the intake of carbon. And yeah, essentially they're able to be quite effective carbon captures until about 35 degrees Celsius. And so this is probably almost the most important in terms of the carbon model because we want to make sure that the seagrasses in question, the seagrass meadows, are actually able to continue this ecosystem service of uptaking carbon for the model to be effective for, carbon to actually be sequestered. So this was pretty good news under our current climate scenario, that Little Cayman seagrass meadows should continue effectively absorbing carbon beyond temperatures of what they experience today. And I believe temperatures can get up to 30 degrees Celsius, but usually around August and not for too many days. So we're still kind of on the up and up in terms of productivity, which is good news. And so finding three is something that was more recent within the last year, 2025. Essentially, we ran these growth studies, specifically using this leaf marking experiment methodology, just taking a hole punch and measuring the distance after about a week or two between, the hole moving up on the blade. It's pretty simple, but it can tell you eventually how many millimeters per day or the growth rate per day that the plant is experiencing through the intake of inorganic carbon from the environment, and again sequestering that and turning it into active tissue growth. And so we found that this rate was about 4 millimeters per day on Little Cayman, specifically in Kingston area. And so this was a pretty interesting finding because I know recently there's more work done within the past two-ish years, believe on Grand, that shows the rates are up to about 3.6 millimeters per day. And generally in the Caribbean, they can get up to six, but that's also inclusive of summer months. So this was a winter month, average conducted in November. So would be really curious to see how these rates could change with summer months, as those are usually a lot more productive, and see if it hits that 6 millimeter per day Caribbean average, or at the height of the Caribbean average. So we'll be running those this summer, and we will use both those rates as qualifiers in the model. And so this is also work that was conducted last summer. Coral skeletons also store carbon, although, not to necessarily the extent that seagrass do, but we can't really rule them out as contributors, especially in Little Cayman, where, there is a lot of reef presence. And with that reef presence comes ability for seagrasses to grow through wave reduction. So essentially, we use this newer method called loss on ignition. And essentially, you first burn away the organic tissue that's present in the coral fragments. and then you do a second burning to remove the decomposing skeleton. And from that, you can get the inorganic carbon that was stored and left over inside the coral skeleton. Um, that was, collected from the environment. And essentially, what we found was that on average, each fragment length stored about zero point zero 0.03 grams of carbon. And so what I think was probably the most remarkable thing about this was the method proved to work very well. This is one of the first times this formula has been used to, specifically on restored corals to measure carbon concentrations. And additionally, there was a very clear relationship between the length of the fragment and the amount of carbon inside of it. So essentially, we can use this zero point zero 0.03 as a unit to scale based on different sizes of coral fragments. So if you see in this image here, each one of these sort of appendages represents one of those coral fragments. And so that can be scaled depending on the length of each of them based on this unit. And so we're looking at per coral head possibly in the 20s, 30s, grams of carbon per coral head, which is, more substantial than you'd otherwise think. And so, yeah, I think this is really cool and that it shows the method worked. And another finding from this was that across genotypes, the amount of carbon stored was not significant. So we can essentially use this model across calcium carbonate, reforming corals to measure how much carbon is being stored on a larger scale. And so this takes me to kind of our final finding at the moment that we have. And so essentially, we've been able to find that coral restoration can enhance seagrass carbon uptake. And essentially, what this means is that the presence of coral structure, restored coral heads actually increases that sediment accumulation in nearby seagrass meadows. And so this was done through using tilt meters, went out, I believe, in February 2025 and did some sedimentary measurements and looking at how dome structure basically influences the sediment around the meadows. And so what they found after collecting depth measurements both at meadows near restored corals and then meadows away from restored corals was that the ones that were closest to the corals actually saw a 40% increase in accumulation by those outplanting dome structures. And so we think that's because, they provide some sort of wave resistance, those coral structures. And so that kind of allows more sediment to accumulate. And that just means more carbon is able to be trapped there. And so this is actually one of the first empirical studies, so with evidence scientifically that has been shown specifically in the Caribbean on these communities. So that's really cool to see, and that makes sense that these ecosystems are kind of working hand in hand to essentially provide ecosystem services and nature-based solutions to help increased biodiversity and leading to kind of a healthy ecosystem. So that was really cool to see that play out. Just as some takeaways, Little Cayman seagrass meadows store more carbon on average, both compared to global estimates and also Caribbean-wide estimates. All three seagrass species can withstand temperatures up to 35, although optimum temperatures are around 30 degrees Celsius. And so we are in a climatically beneficial window for these species to continue um, intaking carbon. So that's also, great for the model. Um, Coral restoration does increase sediment accumulation. So the more sediment there is, the more carbon is able to be stored. Specifically, this happens near seagrass meadows close to coral heads. And that can increase, sediment by 40%. We've also validated how much carbon is being stored within coral skeletons themselves. And probably the most interesting finding was both that this did not vary by genotype, so we can use just that same unit across genotypes of corals. And also that fragment length correlates very closely to the amount of coral carbon that's being stored. So again, we can look at a bunch of different lengths of those fragments and just use that amount per centimeter and scale that out to the different fragment lengths. So that's very useful information. And so just kind of wrapping up with what this summer's work will help us do, essentially putting all of this into context, looking to make these spatial maps to actually get from how much carbon per hectare is stored to how many hectares are there. And we'll also be, conducting another growth study to look at um, what summertime growth rates are to help introduce some variation, inherent variation in the model, and include some of that temperature data that we found as well. And also, as shown here, other variation could include the Caracas network experiment that we conducted last fall using quadrats to essentially get a better sense of the actual composition of these meadows. So going out, collecting data on the different species present, where they are, canopy height, because canopy height has actually been shown to be a large predictor of capture capacity of carbon. So, kind of using some of those species composition, sorts of quantifications to tweak the model and help with those estimates. Because the seagrass meadows are largely thalassia, but there is some variability depending on canopy height, temperatures of the water, obviously for uptake, and just spatial variation. And so the point of this being the bigger picture, essentially, again, is this output that we're looking for is this carbon model that can be used to purchase credits for to offset emissions. And so that would allow this money to flow back to protect and restore these ecosystems and kind of create this positive feedback loop where we can continue doing research and restoring areas that are degraded but might be high in productivity, all while encouraging companies to, be sustainable and support the local communities that they're serving, both ecological and human communities. And so, again, kind of the pipeline we're imagining for this is first measure the carbon stocks. So that's just, again, the FIU data that we have, the sediment cores, and also the loss on ignition study done in the restored coral fragments that we found. This summer will be kind of, moving from how much carbon is there to um, how many hectares there are specifically, possibly doing a time scale analysis over the past 5 to 10 years, depending on the quality of the Google Earth engine data, and looking at how community structure has changed as well, how habitat cover has changed. We've actually kind of witnessed a boom and bust, possibly relationship in the seagrass already, where some areas are experiencing further growth and others are, dwindling out. So with warming temperatures, so that'll be really interesting to take a look at from a time series perspective. Um, Going out this summer also and doing some ground truthing. So running some transects, measuring at the meadow's edge, where does it become sand? Where does it become rubble or, reef? Where are the alive corals? Are there dead corals? Things that you can't just pick up from the mapping layer alone, and you need, physical eyes. And we'll kind of combine that with some of the variation we took last year on species presence and canopy height. And so lastly, the outcome once we have this map together would just be a system level inventory of carbon. So amount of carbon and the amount of hectares. So essentially the amount of carbon that is being actively sequestered on Little Cayman. And at that point, I think we'd be in a really good place to start talking about building a carbon credit model and working with partners to see what that implementation would look like. And I think with phase two that's approaching over this next year, and it might last, I think, 2 to 3 years, depending on, progress. But um, looking beyond just seagrass again, because we're also looking at classifying coral coverage as well, and mangroves as well, and kind of tracing the movement of carbon between these ecosystems and identifying species presence based on carbon, uh, specific carbon prints. And so kind of expanding just beyond seagrass, but looking at kind of the other ecosystem services that are supported by these carbon sequestering communities. And lastly, looking at policy integration, how it would play out when, trying to monetize the model, trying to incorporate it on a political landscape, working with local officials, and also, ideally, this model could be extended to the larger Caymanian zone, but also beyond that into other Caribbean nations, especially since we have a pretty good existing data set with some pretty staple measurements that have been taken already through the Caracas network studies. So I think that provided a great baseline for the kinds of measurements we took here. And of course, we've taken additional measurements here. But just having that framework together is a great step towards, expansion of these ideas and of this framework to, more blue economy and companies that support the environments that they're supporting locally. And so again, just wanted to wrap up and say what's happening this summer. We'll be focusing on satellite imagery, a lot of desk work, um, going out though first and doing some ground truthing, collecting some GPS points and noting habitat boundaries, applying a habitat classification through a machine learning classifier trained based on those images that we have taken out in the field to help us identify sand from alive coral, from dead coral, from alive seagrass and dead seagrass. And that's why we're also going out there as well, because that is not always visible from the map. And there can be swaths of, uh, you know, dead seagrasses, which we've already encountered and have taken note of. And lastly, again, the kind of major deliverable or point on this end would be to take all of that hectares and actually compute the amount of carbon that is being stored on Little Cayman. And that's, would be a snapshot, but also curious to do a time series analysis and see what the net change has been over the past couple years. And so looking forward to jumping into that data set and waiting for, 2026 Google Earth imagery to drop and kind of use the data that we're collecting actively this summer as a baseline for that. And so, yeah, that's my presentation. Again, thank you so much for this funding. Um, it's, I think it's really important work, and it just seems really promising with what we've already been able to do. And so I think just moving in this direction with the map and also, getting to uh, build the model and have ideas for the framework is a really exciting thing. And yeah, just really looking forward to continuing to stay in contact on this project. So thank you.